my name is Sherilyn C. Guadiana, third year BSCS Section F2. Today, I will demonstrate an issue with breadth first search or BFS in our C# search algorithm assignment and show how to fix it. Let me first demonstrate how the BFS and DFS searches behave before applying any fixes. I have set up a small graph in the form of a binary tree with 7 nodes. We will designate the root node as the start node and another node as the goal node. First, let's observe how BFS traverses the graph step by step. Notice that when it reaches the second node, it does not visit all of its neighbors immediately. Instead, it explores one neighbor before the others, which is actually the behavior of DFS. Next, let's examine how DFS operates using the same nodes. Here, we can see that DFS behaves like BFS. When it reaches a node, it visits all of its neighbors before exploring the neighbors of those nodes in depth. This clearly shows that both searches are not functioning as intended. To ensure this works correctly, let's examine the code that implements the BFS and DFS functionality. The classes involved include node.cs, fringes.cs, fringe.cs, fringe2.cs, and search.cs. We will start by looking at the node class. Let me explain how this node class works. The node class represents a single node in a graph, which is used by the BFS and DFS search algorithms. Each node has a name and a value, which can be used to identify it or store any associated data. The class also contains several flags that control its behavior during the search. Start indicates whether this node is the starting point, goal indicates whether it is the target node we want to reach, expanded tracks whether the node has already been visited during the search, and moved is an additional flag that can be used to track movement or state changes. Each node maintains a list of its neighbors using an array list. This allows us to define the connections between nodes in the graph. The methods addNeighbor and removeNeighbor are used to manage these connections. The getNeighbor method returns all the neighboring nodes so that the search algorithms can explore them. The class also keeps track of coordinates x and y, which can be useful for visual representation of the graph. Additionally, the origin property stores a reference to the node from which this node was reached, which helps in reconstructing the path from the start node to the goal node after the search is complete. Finally, the equals method is overridden to compare nodes based on their names, so two nodes with the same name are considered equal. This is important when checking for duplicates or when verifying whether a node has already been visited. Next, we have the fringes interface. This interface defines the basic operations needed for a search fringe, which is the structure that keeps track of nodes to be explored. It declares two methods, add, which adds a node to the fringe along with its origin for path tracking, and remove, which retrieves and removes a node from the fringe for exploration. This is the fringe class, which implements the fringes interface for BFS. It uses a queue to manage the nodes to be explored, ensuring that nodes are visited in a first-in, first-out order, which is essential for breadth-first search. The add method adds a node to the queue and sets its origin to keep track of the path. The remove method dequeues a node from the front of the queue, returning it for exploration. This is the fringe2 class, which implements the fringes interface for DFS. Unlike BFS, it uses a stack to manage the nodes, following a last-in, first-out order. This ensures that the search explores the most recently added node first, allowing the algorithm to go deep along one path before backtracking. The add method pushes a node onto the stack and sets its origin for path tracking. The remove method pops a node from the top of the stack for exploration. This is the search class, which controls both BFS and DFS traversals. It stores all nodes in an array list and uses a fringe to determine the order of exploration. The constructor takes a list of nodes in a type 1 for DFS and type 2 for BFS. Based on this type, it assigns a fringe for DFS and fringe2 for BFS. The main logic is in the search method. First, it searches through all nodes to find the start node and adds it to the fringe. Then, in a loop, it removes a node from the fringe to explore. It first checks if the current node is the goal. If it is, the search ends. If the current node is not the goal, it retrieves all of its neighbors using getNeighbor and converts them to an array. Then it iterates through each neighbor, and for every neighbor that has not been expanded yet, it adds the neighbor to the fringe and sets its origin to the current node. This is how the current node decides which nodes to explore next. The neighbors are added to the fringe in the order they are retrieved. Finally, the current node is marked as expanded, and the loop continues until the goal is found or the fringe is empty. The search one method works similarly but explores one node at a time, allowing step-by-step traversal. The reason BFS does not work correctly in this version is in the constructor. Here, the BFS type is assigned fringe2, which is a stack, and DFS is assigned fringe, which is a queue. This interchange of fringe and fringe2 causes BFS to behave like DFS, exploring nodes deeply first rather than level by level, and DFS to behave like BFS. Now that the fix has been applied, let's run the code again using the same set and arrangement of nodes to see if BFS and DFS functions correctly. As you can observe, both searches now behave as expected. That concludes this video. Thank you for watching.